Hey folks, whoa. Sorry, I'm mic'd up and amped up, and I'm about to, and also, by the way, I'm not gonna be offended if you need to go use the restroom or anything. We've been here for a long time. This is gonna be the first of a series of apologies where I think even the CHI people, I put together what was gonna be a 60-minute talk to find out that, it's a 40-minute talk. So I'm already known for speaking really quickly and having a big slide deck. It's gonna get much worse. The flip side is that the slides are already online. They're on slideshare.net, so you can grab them, particularly if I have to skip stuff to keep you, getting home at a reasonable time. I wanted to throw this up here as well, just because my wife Diana has always been smarter than me and sort of more strategic about her career. We both entered sort of our industrial scientific careers in the mid-90s at Genetics Institute, and she very quickly worked up from entry level all the way up to staff scientist and realized that professionally that was a glass ceiling for her. Without a PhD, you don't really go higher in R&D once you hit staff scientist level. So she decided to move laterally, took on drug program management, and then made the leap into executive leadership. Another example of her being really strategic is that she felt that earning a director title at a billion-dollar pharma would be more meaningful than at a small company. So she earned her director wings at a billion-dollar pharma and then jumped ship to smaller companies. Today, she's a vice president at a gene editing startup. She's got 2 IPOs under her belt, and she's been largely responsible for the company's recent successful IND application. And the only reason I'm sort of mentioning that is that she's also Finnish and very stoic, and just the shit that I've learned from her via osmosis is absolutely horrifying. So, hopefully this is the last time, or we won't have to put up messages like this, but yeah, we need to get better. All right, so I'm going to skip the intro stuff. This is really for the people who download the slides. I'm also a little bit nervous about time. I am going to put up my newly, trademarked thought excreter magic quadrant here. This is the part of the talk where I really try to desperately tell you that I'm not an expert. I'm not speaking on behalf of our huge, industry. This was alluded to earlier in the panel. One of the cool things about consulting is we get to see how lots of different environments operate. And in particular, we tend to be a little bit more free to speak. We can talk about what we see. We can talk about our experiences. So the reason why you have people like me coming up and doing these types of talks is not because we're pundits or thought leaders. It's because we see a lot, and we're generally allowed to, we have a little bit more lateral freedom when we come to speak. So this slide is also in the similar vein where, this is a huge and diverse world. I do a lot of commercial pharmaceutical and biotech projects. I'm less exposed to big government gigs. I'm less exposed to academic environments. So I am, the stuff that I'm going to try to tell you today is really sort of biased by my work. And so you need to sort of filter that through your own BS filter or through your own sort of particular set of business and scientific requirements as well. So I'm going to start off first with sort of a catch-all bin of, in my consulting work when I do technical writing, I have a section called observations, and that's where, things that I think are useful to convey that don't necessarily rise to the level of actionable recommendations, or in this case, sort of real measurable trend. So the first thing I really want to talk about is, I feel sort of that we've navigated the entry into this sort of data-intensive science era relatively successfully. I still feel compute is a tractable problem. I still feel that networking, while it has its pain points, it's at least solvable with money and a little bit of engineering. Storing a lot of crap is actually fairly easy. The hard part is actually understanding what we have, managing what we have, understanding the value that we have. But that's really one of the central problems that we're dealing with right now. And sort of that white little text block there is, walk the trade show floor. How many vendors at Bio-IT this year are selling data management, data discovery, data handling, and data curation systems? It's like 3 or 4 rows of the trade floor. It's an acknowledged significant problem in our world, and it hasn't gone away. So the other thing that we're sort of finding, and also, by the way, when I do this talk, I have pictures that represent the younger, thinner me, and a picture that represents the older, graying me. And so I want to start comparing and contrasting things that I've said in prior years with today. So, in prior years, a lot of my consulting work was teaching IT that computers were a digital laboratory. I can't tell you how many times I ran into an environment where a really, expensive PhD-level scientist was not allowed to install R on her laptop because IT treated it as just an endpoint for performing business functions rather than a digital laboratory. We're sort of past that now, but one of the issues that we're starting to see is that, from an executive leadership management, from outside R&D, people still view sort of scientific computing and the capabilities around it as a cost center to be minimized, rather than something that's actually going to distinguish you from your competition, allow you to survive the sort of next era. And in particular, one of the things that we're starting to see is the failure of HR to capitalize on your internal capabilities for employee recruitment and retention is actually fairly significant. And I ran my slides through BioTeam, a couple of minutes ago, because I really do write these slides at the last minute. And the feedback from BioTeam was fairly positive. We are definitely gathering data in our consulting work that if HR doesn't talk about it, or if HR is not tracking it, your employees are and your scientists are. And we know who's got a crap IT shop. And that is going to affect your recruitment and your retention over time. So the other thing, quick a little bit about user trends is there's two trends related to users, particularly users of sort of scientific computing environments in pharmaceutical biotech. One is the user base is climbing rapidly, and it's a combination of both new domains, but also the percentage of scientists who are being chased off of laptop scale analysis has been really growing dramatically in the last year or two. So more and more of the people coming into my scientific computing environments are people who for decades have been productive researchers, but they've always been able to work within the realms of the machine that's sitting lab side or in their desktop machine. The second trend is we have the simultaneous problem of gaining and onboarding users who are both simultaneous. Well, actually, the users are different. We have more less sophisticated users, but we also have more very sophisticated users, and it's becoming a little bit of a support burden to handle both. The unsophisticated users coming into our environment are, like I said, the people who are being chased off of laptop scale environments. The more sophisticated people, we've been doing this for a long time. I've been doing this for 20 years. Most of the people who are on the panel have been doing this for a long time. The early career young scientists that we're hiring and that we're recruiting and that we're bringing into industry, they're already coming in with cloud exposure. They're coming in with HPC experience. Many of them have exposure to national labs or supercomputing environments. So we have this simultaneous problem. And then the worst thing from a support perspective, I think, is we are fairly good at onboarding novice people, and we're fairly good at handling experts, because what you do with an expert is you stay the hell out of their way. And IT is pretty good at staying out of the way of the expert. What we're really sort of failing to do is catering to the intermediate people, and in particular, taking an effective person who is sort of an intermediate level of scientific computing and helping her advance to sort of the expert level. I think that's the biggest gap that we see right now in trainings. We can onboard the newbies really, fairly well in most cases. When we have an expert, we just stay the heck out of their way, and all is good. There's a sort of major capability gap in taking the people who are effective but could be vastly more effective if we sort of help them sort of become expert scale in their work. The other thing that we're starting to see is the definition of HPC is being stretched, I would say abused. There's a lot of environments where you have this problem of users being chased off of laptop scale analysis solutions, but the R&D organization is the only place where you can find big compute, big memory, big storage, GPUs, and things like that. So there's a little bit of a dangerous trend that we're starting to see where HPC or scientific computing is becoming a dumping ground for problems that don't fit on cheap rented laptops. And so the issue there is not necessarily that we're, to a certain extent, adding workload diversity is not really a huge problem. It becomes a huge problem when you have to detune your specialized environment to support the generic demands and generic requirements that are coming out of this sort of parasitic use case that we're starting to see coming up. So this is either a real bit of useful information or it's a sign that I'm really stupid. I haven't had to care about compilers and tool chains in a long time. It's been a decade since I played with Portland group compilers and things like that. That's actually very, very different. And the biggest driver for me has been the past couple of months of fooling around with cryo-EM workloads. Compilers and tool chains matter. And in particular, if you talk about, or if you remember my talks from prior years, one of my existential sort of meta picture or meta issues was that the rate of lab side instrumentation, the rate of innovation on the lab side is changing far faster than IT can keep up. I think what we're starting to see is the rate of innovation in our software and our scientific codes is also hitting that acceleration point where the state of our software art is advancing faster than IT can curate and maintain the developer and the execution environment. And this is a long-winded way of saying that versions of glibc matters, compilers matter. You probably want to start looking at things like the Intel commercial compilers because you could probably squeeze some advantage about them. And really, like I said, this is either obvious to you and a sign that I'm a moron, or it's relatively new. It's been at least a decade since I had to care about this stuff, and now I really do have to care. So this is the sort of a summary here, is that a modest investment in a commercial compiler set, a modest investment in sort of looking at your tooling and your execution environment relative to the cost of the latest CPUs, relative to the cost of NVLink, and relative to the $300,000 cost of a GGX2, you can actually squeeze some pretty good return on investment out of a modest sort of relook at your sort of development and toolchain environment. So this is the other thing here. This is a little bit homework for you. The prior slides were driven by the fact that the open source tool for cryo-EM workloads, one of the popular ones is Relion. I built Relion on CentOS 7 with the GCC4 tooling, the stuff you get out of the box. I built it again with the GCC7 dev tools, and then I built it again with the Intel commercial compilers. The performance difference between those three was so astonishing that I'm too afraid to put the numbers up here because I think I might have made a mistake. But I talked to some experts and I might have made a mistake. So really, particularly if you're interested in this or you don't believe me, I'd encourage you to do this cryo-EM homework, build it on 3 different methods, test the time for yourself, and you'll see very, very significant performance differences. So related to cryo-EM, this is where I'm going to gripe about the state of cryo-EM benchmarking and hopefully send out a call for help. While doing a bunch of cryo-related workload testing for BioTeam, we realized that, first of all, everybody's just benchmarking CPU and GPU performance. They're not really looking at systemic, multiple concurrent use, how it affects networking and storage and data movement. But the worst thing about it is everybody is testing with a 50 gigabyte data set. Do your Google searching, read all the papers on cryo-EM, rely on benchmarking. They're all using the same data set. The data set is shockingly tiny. It's small enough to fit in physical memory. It's actually small enough to fit in the GPU memory in certain nodes. And I'll just highlight the sort of white text there. Realistically, how many of you dealing with imaging workloads are working with 50 gigabyte or 60 gigabyte work sets? I sort of truly believe, and the problem is that this tiny benchmarking set is being used by the people who are trying to sell you expensive stuff. So I'm putting out the call. This is kind of a call for help. BioTeam really is looking for multi-terabyte cryo-EM data sets, things that we can drop into 2D and 3D classification runs. And I think the community and the sort of state of the art would be advanced if we move away from these sort of 50 gig data sets. So if anybody's out there, we'd love to talk to you. We're really looking for, it's got to be shareable though, because we don't want to do this in secret. We want to sort of host it, distribute it, publish it, share it, and really write about sort of realistic, image-based workloads and their effect on CPU, GPU, and sort of large-scale storage systems. So moving on to sort of another quick trend where machine learning and AI is definitely one of those things that's sort of real and transformative. But the interesting thing here is that the race to acquire or generate data, I think, is the potential to become ugly. And we've had some sort of ethics and data privacy issues in our space before, and I think one of the potential things to watch out for is, you're going to live or die on the quality of your training data. And I think there's going to be extreme pressure on getting the biggest data, the best data, and getting it in-house. And there's the possibility of some people taking some ethical shortcuts, to getting that data that I think we need to watch out for. One of the more interesting examples and innovative things that BioTeam has seen, in the last couple of months in terms of getting access to high-quality data is we've seen a couple of organizations doing this thing where they put something out on the internet for free. In this case, it was a particular set of cloud-based analysis tools. In exchange, there was an opt-in process that would allow the users of that service to share the data. The end result is for this particular organization we're working with, they're getting 30,000 MRI scans a week that are opt-in, that are metadata tagged and ready to be dropped into sort of medical and clinical workflows. So that's the type of effort that people are going out to actually acquire the data that we need to feed into our machine learning, AI, and sort of deep learning frameworks. All right. Moving on a little bit, and I'm going to, this is a little bit of a downer section for me, but I think there's some problems for us coming up ahead. This is I can't name her, but this is a quote from a very senior leadership a person that I had some time to chat with, and really, I think a lot of this is obvious. The unit cost of storage in our world is going down. It's great to see that, but it's not going down as fast as the rate at which we can consume or generate more data. On top of that, the actual cost of running a sort of sophisticated biomedical computing operation continues to grow. And for many cases, the ongoing annual increase in cost are greater than the annual sort of increase in your mission budget. So this is a particular national institution that is actually having to cut research mission in order to sustain sort of critical capabilities that they're having. And so, again, this old icon represents stuff that I was saying years ago. Years ago, when I was talking about triage and throwing stuff away, it was a real storage focus. Years ago, we were saying it's okay to delete data because if you can go back to the -40 freezer and repeat the experiment, that's totally valid. So, in prior years, we were talking about deleting, data is okay as long as it was being done by science. Again, the mandate here is IT never deletes scientific data. This always has to come, from the R&D organization. So that was kind of a narrow focus a couple of years ago. The issue that I'm seeing in sort of 2018, 2019 is compounded. The easiest way to distill it is that there are now individual scientists who are completely capable of swamping a leadership class supercomputer, or even something weird like an exotic like an Anton 2 for molecular dynamics, with completely valid scientific questions. So I'm an IT person. My sort of joy in life comes from building infrastructures that enable discovery-oriented scientific research. But I'm at a point now where a single person asking very, perfectly reasonable questions can completely obliterate anything that I can reasonably build and deploy. That's not going to scale. That's not going to sustainable. Something's going to have to break. And I think what's going to happen is, in the same way that we saw sort of data triage and the acceptability of sort of deleting data, I think we're going to have to sort of stop half-assing around governance. I'm going to say words like, we're going to reduce scope, we're going to tighten scope. Management will say something like governance. But I think what's going to happen here is we're going to have to get serious about this. The problem of a single user being able to swamp a system of arbitrary size, I think, is real. I think from a sort of business perspective, we can solve that with governance and procedures and processes. But I'm a scientist, and this sort of concept of, or I was a scientist, this concept of rules starts to chafe against me, and I get really, my management radar goes up when someone says the G word in governance. And so I'm thinking a little bit about moonshots and open-ended research. And I'm trying to figure out how we support the truly innovative stuff in a world where we might have to put some constraints around our computing capabilities. And all I can really think of right now is what the national labs seem to be fairly successful in terms of how they allocate grants in the forms of allocations that basically you're free to use however you want. So one possible solution for the sort of open-ended moonshot and sort of truly innovative stuff might be to move to a system of internal grants or allocations that our scientists can spend however they see fit. In order to get through these lean times, we actually need some stuff. If you don't have this stuff, it's going to be a fairly disastrous process. And really, it boils down to is having the metrics, having the true operational cost, both for on-prem and cloud. And you need to be able to log what tools are being used when, so that you can start building, rules and procedures and sort of a nice little framework around how you're allocating the increasingly contested for resources within your sort of scientific computing framework. The flip side of that is the same people that I've been talking to about these doom and gloom scenarios, and I wanted to end this section on kind of a little bit of a positive note, is there is some value to lean times. In particular, it's the lean times that allow you to blow up silos. It's the lean times that allow you to sort of decrust your infrastructure and your org chart. It's the lean times that actually force competing organizations to come together and agree on APIs and middlewares and sort of common ways of doing things. And the final quote was really interesting from a leader, is that it was the lean times that made them think really long and hard about how to run technological operations in a different way at a much larger scale. So, all right, that was the end of the sort of basket of individual observations. I want to talk in a little bit where, again, in the same way I found that I didn't really care about commercial compilers until relatively recently, it's interesting that now I have to care about hardware and silicon again. So, years ago, or even a couple of years ago, Intel ruled the world. Compute was a commodity. It costed the same, a few percentage points, no matter where you got it from. And the only thing we really saw in the GPU world is that we were starting to see a divergence in GPUs in that we would use different types, a different class of GPUs for the people who were doing VDI and visualization, and a different class of GPUs for the people who wanted to do chemistry and structural biology and MD simulation. That's flipped around in 2019. Now I have to care about CPUs, now I have to care about GPUs, now I have to care about weird things called TPUs. Bottom line, on the IT side, we've got to revamp and rebuild our benchmarking and sort of proof of concept teams. That's really what it's going to boil down to. And to sort of summarize it up here, the reason why hardware is starting to matter again in my world is that AMD is back in a really serious way. Both their roadmap and their pricing is really, really interesting. You're going to start to see some competition between Intel and AMD. I mean, you're already seeing it. The GPU stuff is really interesting. The problem right now with GPU management in research computing is the sheer diversity of GPU distributions that we need to handle. We have certain workloads that really want to see one GPU in a chassis. We have other workloads that really want lots of memory in a GPU and others that don't care. NVLink and the sort of exotic links between GPUs are really expensive, so you have to be sort of careful and strategic in how you deploy them. And so at the end, and then the last problem, I'm going to complain about this a lot, is that it's kind of a pain in the ass to get the GPUs you need out of the cloud environment. They are heavily contested, highly sought after resources, and if you can't get the GPUs out of your cloud vendor, that's kind of a problem. And I'm going to skip the TPU and FPGA stuff, except to say that in the same way that CPUs and GPUs are becoming more impactful in our sort of IT and research computing world, we now have cloud vendors and hardware vendors trying to differentiate themselves in the machine learning and AI space by building custom silicon. So now we actually, and the worst thing about that is that now that you've got the custom frameworks and the custom hardware into play, now we have to care about their software frameworks and their development environments. And that actually means IT has to have a deeper engagement with the users, because it's no longer just an ROI or a cost analysis of this is the cost of hardware X from vendor Y. We actually have to sit down and gather requirements from our users. I really care about the software development and framework requests that my developers have, and I need to factor that into the real world costs of TPUs, GPUs, and custom silicon as well. So, quick hit, couple of slides on facility and infrastructure. The probably obvious answer, yes, you still have to do the math. We're still doing the math all the time on on-prem versus hybrid versus cloud. I'm still in the camp when it comes to persistent 24/7 scientific workloads. The economics still favor on-prem. The giant asterisk there is that economics is not the only driving factor. The single biggest driver for cloud is capability, and so depending on how you weigh capabilities and actually novel capabilities as well. So the single biggest thing with cloud right now is compute is easy, elastic compute is well understood, serverless is going to be transformative, but the persistent month-over-month cost of petascale storage on the cloud combined with the egress fees is really what makes the economics challenging. That's sort of where I'm at. And that sort of economics challenging is sort of paying into this particular trend that we're starting to see is starting to see a lot of co-location projects, either people buying entire suites or just putting a couple of racks or two to aggregate their cloud traffic or aggregate their DR infrastructure. A really good sign of the times is, a good friend of our world is Steve Lister. Steve got poached from Novartis and is now a CTO at Markley Group because they sort of recognize the need of that type of skill in the sort of colo world. And so the drivers for that are there's a lot of data centers that people are trying to figure out, does it make sense to retrofit or should we just move into a more modern suite? The cost of new builds is incredibly expensive. BioTeam's been playing with new facility construction for some projects, and it's tens of millions of dollars, and you usually have to build more than one facility. So the sort of major drivers in addition is there are some advantages, even for cloud scale people, to have a co-location cage or a co-location suite when it comes to aggregating your cloud traffic, when it comes to aggregating your multiple partners, when it comes to actually spinning your traffic across multiple cloud environments. There's a couple of venture firms that have a design pattern involved that when they spin out a new portfolio company, they all meet in a co-location suite so that they can exchange data and exchange network traffic if they mean to. So there's some interesting trends regarding, we're not entirely on the cloud yet, and a lot of the drivers are on this slide here. So this is one particular, I like to give you my horror stories of things that I don't like to see overwrite. So this is legitimately the dumbest thing I saw in 2018. I wish I could tell you where it is, but I think there would be some hurt feelings. So I'm just going to say that there are some fancy top-tier incubation innovation spaces in Boston that are designed to attract the latest pharmaceutical and startup companies. However, when I walked into them, the words are up there. The long and the short of it is that they give you lab space, office space, reagent management, and shared instruments. You're not allowed to install a damn piece of hardware. The Wi-Fi is shared, the Ethernet is shared, the internet access is shared. And if you want to change that, if you're a data-intensive company, if you're building an exotic instrument, if you're doing a lot of robotics or automation, it's a three-way negotiation involving the operators of the innovation space, the leaseholder who actually owns the floor where that innovation space is, and the people who actually own the building that everybody else is leasing all of that stuff from. So for me, and I'm so upset about this, I had to make 2 slides. To find to find a pharmaceutical startup space that assumes all we need is, Wi-Fi controllers, domain controllers, and a sprinkling of managed IT services, it's just ludicrous. Someone's either, that means either you've been listening to too much of the telecom and cloud marketing or you fell asleep on a pile of CIO magazine. It's just flat up wrong. It's offensive to me as an IT person to see, a brand new fancy space operating in this manner. And I gather there are completely agile companies out there that don't need that stuff, but we need infrastructure. We're buried in data. Our instruments are generating data. We've got USB-attached genome sequencers now that are shooting out data, and to build an innovation space that has no concept of that or no awareness of that just is incredibly offensive to me. So sorry about that. That's my rant. Dumbest thing I've seen in 2018. So moving on, I want to talk a little bit about org charts and scientific support. And this is because this year I've had a chance to talk to really, really large environments, people who are sort of going head-to-head with national labs and sort of DOE type stuff. When you start comparing life science to other HPC and supercomputing environments, one of the things you find is that what differentiates us is actually the sheer diversity of our workload. There are other supercomputing domains where you might have huge data, giant problems to solve, but the domain is encapsulated by less than a dozen codes that are well profiled, that are well engineered, that are incredibly performant, and we know how to design and tune systems for them. The differences about life science is that we have the same user base, we have the same giant computational problems, but we have hundreds and hundreds of applications. But even I don't want to say the word worse, but the distinguishing characteristic in life science is the sheer number of domains that we have to support. Each domain has different technical requirements. Each domain has different infrastructure requirements, and within each domain there are subdomains that require very, very, very deep expertise. For every one of those domains, there's someone who wants to do that on a particular pathway or a particular organism, or for a particular large-scale study or for a particular small-scale study. When it comes to supporting scientific computing at scale, I don't want to use the word special snowflake or special and unique, but this is a case where actually life science, when you do an honest comparison of supercomputing and high-performance computing, we are quite different. And I'll say the last sentence is the real thing. The domain and workload diversity and our crap code is the distinguishing characteristic of a life science workflow. Talk to the operators of the supercomputing and the national lab sites, and they'll tell you the most common cause of crashing the cluster or crashing the file system is someone trying to do something weird with genomics or bioinformatics. It brings the whole system down. So really, what this is starting to see is this is changing the look and feel of some of our support organizations. And what we're starting to see is the level of domain expertise required is too much for a central support organization to have. So you're starting to see the domain expertise move back into the stakeholders. It's moving into the lab, it's moving into the PI, it's moving into the R&D organization. Conversely, what you're starting to see is the centralized scientific computing organizations are really taking on responsibility for the enablement services that are truly cross-domain, and in fact, they're cross-company. So that list there, by reorganizing your support and your service organization across capabilities like data engineering, data science, data visualization, having a couple of people around who can get deep into firmware and write CUDA, that's the type of stuff that we're starting to see sort of coalesce within the centralized scientific computing organization, where the actual very, very narrow domain level expertise is sort of spreading out to the edge of the organization. And this is happening enough that BioTeam, we're starting to see the words and use the words kind of service-oriented organization, service-oriented delivery. And really what we're starting to see is reorganizing our org charts around the actual scientific use case and the end user requirements, and not building org charts that are siloed by technological skill or technological requirement or a particular type of technological operation parameter. So it's a good way to blow up silos and move to kind of a team of teams approach. And we're starting to do more of this sort of organizational assessment work, and I think you'll start to see that influence future talks from me and others at BioTeam over the years. It's actually quite interesting. All right, so time-wise, I think I'm doing okay. I'm going to get into storage, compute, networking, the stuff that was sort of the bread and butter of other trends talks. And the interesting thing about storage here is, this was me every year for the last couple of years. Everybody needs peta-capable storage. The number of people who will actually consume petabytes is indeterminate, but you need peta-capable because you don't know if you're going to be in that community. We always throw up the scary graph about consumption. But the most interesting thing is I gave a lot of advice around how within bioinformatics and genomics, if you talk to a scientist and explain, I can give you lots and lots of space, but the caveat is that I'm going to have to give you a slightly slower storage system. We would always trade performance away in order to gain capacity, because a couple of years ago, capacity was the existential dread. We were always worried about running out of space, and we would trade off a little bit of performance to get that. At least in industry, I didn't see a lot of parallel file systems because of the complexity and the operational burden and the sort of parallel skill, the sort of specialized skill set that you needed. And I was still sort of saying that it's easier. The friction required to generate or acquire vast amounts of data is still smaller than the cost and effort required to sort of keep that data safe, available, and durable over the long term. So that was kind of what I've been saying for years. This is the stuff that's relatively new. The biggest piece of information that I can impart to you, if it's not already obvious to you, is that the capacity and performance calculus has swung back the other way in a major way. Machine learning, AI, deep learning, and image-based workloads are requiring very fast, very performant file systems. The flip side is we still need very, very big storage systems, because if you're doing machine learning or AI work, one of the requirements is you need to have all of your old input, all of your old model, and all of your old training data around around because you're constantly retraining, rebuilding, and revalidating your data sets. So the biggest change in the storage landscape now is that we can't make performance trade-offs anymore if image-based workloads, machine learning, or AI are sort of part of your mix. That's kind of a sort of big sea change for us. The other thing that's happening is the dominant file type is becoming imagery. We're moving away from having the dominant file type be sort of genomes and sequences, and now it's lattice light sheet microscopy. It's pictures coming off of 2D and 3D ultrasound, and it's things like cryo-EM microscopy. So the contributing factor here is, there's going to be some interesting stuff happening, I think. There is a tremendous amount of storage, I think, that is coming off of end of life or entering year 3 or year 4 of a support contract, combined with some really interesting companies have entered the market with both either really interesting capabilities or truly sort of advanced next-gen architectures. The other thing is from an industrial, commercial, pharmaceutical, biotech bent, parallel file systems are a lot more attractive now because of the need for performance. I'm willing to look into the administrative and operational burden of a parallel file system in order to get the performance that I need to support my new class of scientists doing ML and AI work. This is the other thing that we're starting to see is if you ask around in your company and you have scientists or even worse leaderships who sort of have this default stance that all of our data is important, that's actually worse than the honest answer, which is we don't know how to figure out which of our data is important and what's not. A major issue within organizations, particularly at the petascale, is trying to treat all data equally or not doing the due diligence to require, sort of figure out what data is truly valuable and what data could be maybe shifted to a different tier or even punted entirely. This is going to lead to significant overspend, significant operational overhead, and tremendous amounts of wasted money. At the end of the day, it's about the data. It's not about it's about the data, not the storage platform. We're running into issues with sort of data hoarders and people who are sort of promoting this ethos that all of my data is important. You have to put it on the tier 1 storage system at all times. That type of attitude can't sustain, particularly at the scale that we're generating data and sort of consuming resources on our storage platforms. So this is another thing I used to say years ago. I was a big fan of single namespace storage because I thought if you didn't give scientists a single pool of their data, they would do wildly inefficient things like storing the same data in 3 different locations. You would end up with issues of data provenance and questions. And so for years ago, I was really into the idea of it should be IT's job to provide a single, consistent global namespace. We should try to do all of the tiering and all of the magical stuff so that we don't have to bother the scientists. I'm over that. So I think in general, I think we've done a bad job at encouraging users to actively take responsibility for their data. I think we have the stuff that IT should be doing is the data protection against disaster, the data protection against a facility fire. It is still wildly inappropriate and in many cases impossible for an IT person to make a decision about how to classify a piece of data, how to set the retention policy on a piece of data, how valuable is a piece of data, can it be moved outside of a geographic national boundary for GDPR reasons. More and more of our data handling has to move back onto the hands of the researchers and the people who are working with it. So my biggest attitude change here is that I no longer have patience for scientists who have built a career and a publication history of being data-intensive scientists who now come to IT and whine that it's not my job to manage data, it's not my job to move data, that's an IT job. No, scientific data is your job. The responsibility has to land to you. If you are required, I know I'm an IT person, so it's kind of easy for me to sort of say this, but I think the fundamental failure is that IT tried to glom onto the single namespace automated management stuff, and in exchange, what happened is that we sort of deprioritized the value of having active hands-on curation of our scientific data. And I think that is going to change, and it's going to change because we're running out of space. We don't have the money to store everything forever. The rate of data generation is blowing away. I think long-term, and hopefully sooner rather than later, the responsibility of data management is now with the scientist. IT's job is to have a business and scientifically appropriate platform. Our job is to keep the system available, reliable, and durable. But the actual act of moving, tagging, curating, lifecycle managing, got to go down to the scientists. And that might actually involve, oh my God, you have to move data from one location to an archive tier. Yeah, suck it up. That's basically your job at this point. So the one exception that I want to say, because I spent like 3 minutes slagging on scientists, is that there are certain exceptions where it is an absolute waste of valuable scientific training and time to have a scientist involved with some aspects of data. And for me, it's the large amount of physical ingest via disk drives. If you've got a scientist who's mailing a disk drive or two around to collaborators once a month or once a quarter, that's cool. But if you're ingesting or dealing with large-scale physical movement of physical media, that is a fantastic waste of a scientist's time. That is one example of something that needs to be operationalized, put behind an SOP, and sort of delivered as a service by the IT organization. So that's the one example of where you don't want scientists, and scientists should not be sort of managing the data. So for me, this is kind of the social contract, and I think I'm going to skip this slide because I've already talked over it. Like I said, my job as an IT person is to design a system that will keep your data safe, durable, and reliable, and it will also meet the business and scientific requirements for both size and performance. I think it's the end user responsibility. Oh, and also my other mission, and this is another thing where IT has failed, is delivering the proper metrics, monitoring, and most importantly, I can't slag scientists and demand that they manage their data better if I don't give them the tools to do that effectively. So that is on IT. That is our job to actually do. But I think the actual day-to-day responsibility for ownership and curation of that data, it's got to move into the R&D organization, move explicitly under the sort of remit of the scientists and the scientific users. I'm trying to think of, putting it all together. I think I'm just going to, really what I'm going to talk over this slide is that I think there's an interesting time for the storage landscape driven largely by the fact that the performance pendulum has sort of moved in a big way. I think there's some opportunities for enterprise to sort of move into the parallel file system space. I think there's going to be a lot of storage platform switches over the next couple of years, and it's going to be interesting to watch. And finally, I'm cool with multiple tiers and namespace and making end users a little bit more responsible for managing stuff. I'm going to, if I had given this talk earlier in the conference, there's a bunch of interesting people that you should go talk to, but I think right now the booths have been destroyed, like the trade show is no more. So, I'll leave this in for the, for the people who download the slide, but there's a bunch of really interesting companies out there that you should go talk to, particularly if you're sort of, on a storage landscape journey at the moment. So networking is interesting because I've only got one slide on it, but it's still the #1 pain in the butt when it comes to my consulting work. So the real issue here is that not a lot has changed since I gave this talk in 2018. Moving vast amounts of scientific data across networks is still very, very problematic. We're doing a bad job at efficiently rolling out 40 gig and 100 gig networking. We've got enterprise IT that's concentrating on the data center rather than building out connectivity to our labs and floors and switches. We haven't really done, we know Science DMZ works. We know Science DMZ design patterns work, but there's still a lot of work to be done in actually separating the business network traffic from the science network traffic. And finally, last but not least, our connections to the outside world are too small, and our firewalls and security controls are still biased towards the way businesses consume the internet, phone calls, web browsing, things like that. And they really do still melt down when you try to move a massive amount of data through them as a single monster flow. Honestly, the biggest, most shocking thing in the networking space for us, I think, was NVIDIA purchasing Mellanox. Like, at the end of the day, I have a lot to say about networking, but the summary is it hasn't really changed a lot for me since 2018. All right, so moving on to cloud, and there is a brief chance I might either finish on time or like a minute or two later. Cloud is short. This is what I've been saying years ago. Cloud is a capability play for life science organizations. Saving money is not the primary driver. That's really what we've been saying for 10 years. Cloud is all about capability. It's either because you've misaligned your internal infrastructure and you're no longer meeting the needs of the scientists because their requirements change every 6 months, or it's because there are things on the cloud that you simply can't do on-prem. Lambda, functions, serverless, event-driven stuff, some transformative stuff there. The change in message here is that about that cost savings thing, what you're going to find is that serverless computing is both transformational in terms of how it affects the way we deliver science to end users, but it's actually transformational for cost too. The economics are very, very compelling. There's a really interesting paper you should read, the Berkeley paper. They did an original one 10 years ago about cloud. They've got a new one out where they're talking about their view of serverless computing, and I think their cloud paper has been cited like 15,000 times. I think the serverless paper is going to be cited in about the same way. The caveat here is that you got to watch out for the cloud marketing people and the people who are all about Lambda and serverless, because a lot of them come from an attitude where everything can be containerized, everything can be distilled to an API, everything can be built into a microservices architecture. A lot of these people just have no concept of science. They have no idea the sheer number of Perl and Python scripts that we run, and they just really have no idea about the sort of human and interactive effort involved in discovery-oriented science. So this is part of me being a huge fan of serverless and saying it's going to be transformative, but this is also one of those things that not only is it overhyped, but you have to weigh the marketing message against reality. And the marketers are going to come at you from an attitude that anything legacy should be thrown away. We have no idea about publication and data retention and making data available. They want to throw everything away, put an API on it, put a service mesh on it, and call it a day. And that's actually not going to happen in our world. All right. The only other stuff that's really been interesting, I don't know how many of you saw Jason's keynote. Microsoft's acquisition of Cycle has really started to pay off, in particular on Azure. They've got some really interesting capabilities, particularly if you're interested in high-speed, low-latency interconnects or bare metal iron. The other thing that's really starting to happen is because of the AI ML race, companies are really trying to differentiate themselves from each other. And that means all of the companies are building custom hardware and custom silicon. And that's just going to make, it's not really a lock-in thing, but again, it's a tooling, an ROI. It's sitting down with your developers and figuring out which one of the AI frameworks do you want to use, and sort of IT sort of building an additional relationship with the users to figure out which one of these environments is going to provide the ML framework that we need. And then finally, I do have a major gripe, and the reason why I feel justified in saying that is it's been consistent across a couple of different projects I did in 2018. Everybody needs GPUs, and they're becoming very rare and scarce commodities. I gave up on trying to put GPUs in Amazon placement groups a long time ago. Now I can barely get the number of GPUs I even need, even if I relax all subnet and all placement group restrictions. So it's a little bit of a problem to watch, and then actually the GPU scarcity might drive some of those co-location and on-premise decisions. Not being able to get GPUs or not being able to get GPUs in a timely manner or in a cheap manner starts to make the cost of that $300,000 DGX2 device a little bit more palatable. So it might actually start driving a little bit of cloud pushback as well. I think I've got 22 seconds left, wrapping up. At the end, I don't want to read this slide. This is just kind of a sort of summary of all the stuff I've been trying to impart to you. But at the end of the day, I think the major issues here is the rate of storage consumption versus the unit cost of storage is still a problem. The other big thread I've repeated, repeatedly is the performance pendulum has swung back to performance. That's going to change a lot of our storage design and storage architecture decisions. We're starting to see scientific use cases that can swamp even sort of leadership class supercomputers. The facility and sort of data center stuff is interesting. There's a little bit of a trend moving back towards co-location or on-prem. And then finally, what really makes us diverse from a support perspective is the sheer diversity of our workload, the sheer diversity of our domains, and the impact that has on both our org charts and the ways we sort of choose to support those scientists. And I think I'm done, and I am 29 seconds over time. The other thing I wanted to say, actually, so I've been trying desperately to get out of this talk for a long time, so we crowdsourced solutions and questions, and I really want to acknowledge everybody who took the time to respond and sort of provide feedback. And then, like Chris Dwan was saying, next year is the 10-year anniversary of this sort of trends talk, and so you can probably expect people to be reaching out to ask, what you want to see next year. I really like the idea of the panel and the talk, but please be blunt with CSI. Please be blunt with the conference organizers and let them know what you want to see next year. That's it. I'm 59 seconds over. Thank you guys very much for your time. Oh, and I think finally, for the betting pool, there's 62 slides in 40 minutes, or 41 minutes. So thanks again.